Hello everyone and welcome back. In this lecture, we're going to continue where we left off in projections and coordinate systems by understanding how we build geographic coordinate systems or GCSs based on datums, coordinates, and central meridians. Parts of this lecture might be review from your geography lessons in school, but it's worth contextualizing the rest of projections and coordinate systems with this information. To start, let's take a look at how we've laid out the Earth from a coordinate perspective. In a geographic coordinate system, we talk about meridians and parallels. We define this based on the poles, with meridians converging at the poles, necessitating the angular coordinate system. The lines aren't a constant distance apart, but they are a constant angle apart. These are the lines of longitude that comprise the x-coordinates in a GCS. Parallels, on the other hand, are parallel and never converge. They are a fixed distance and angle apart and represent our lines of latitude comprising the y-coordinates in a GCS. Once we have our Earth model, or datum, we can start building coordinate systems. To do that, we need to define our central meridian. That is, a north-south line that, along with the equator, defines the origin of the coordinate system, or the equivalent of the point 0, 0 in a Cartesian grid. We usually use the Greenwich meridian, sometimes called the prime meridian, which runs through Greenwich in the United Kingdom, as well as parts of France, Spain, Algeria, Mali, Burkina Faso, Togo, and Ghana. Where the prime meridian meets the equator, we get the origin point of the coordinate system. From there, we can get x-coordinates along the lines of longitude that are positive, moving eastward all the way to 180 degrees in the east, and negative, moving westward to negative 180 degrees in the west. To get the y component of the coordinate, you can go between 0 and 90 degrees up to the North Pole, or 0 and negative 90 degrees to the South Pole. These two together help us locate places anywhere on the Earth. Knowing that x values can be between negative 180 and 180 lets us define what's called the domain of the x-coordinates. The domain says that all values between negative 180 and 180 are valid, but values outside of that range are invalid in the coordinate system. This is often used as a descriptor for datasets and coordinate systems. We can construct the range the same way by using the valid y-coordinates instead. In practice, in GIS, the domain is usually the full set of valid x and y coordinates for a dataset. ArcCatalog, for instance, will report to you the dataset's domain in the Properties panel, which may be a subset of the overall coordinate system domain. Now, while we talk about latitude and longitude as if they're some absolute truth, they're not just one coordinate system. Remember when we talked about datums? It really depends upon which datum you build it in. Remember that the same coordinates exist in multiple datums, and it's at a different location on the ground in each one. There's not one true coordinate system for any location, just a true location for a given coordinate system. We could theoretically build another geographic coordinate system that uses a different coordinate system overlaid on top of a datum, but in practice, I haven't used one that didn't use the mix of angular units and degrees to cover the Earth in coordinates. So, to recap, in this lecture, we learned how geographic coordinate systems are constructed from a datum, a coordinate system, and a central meridian. Next lecture, we'll use these geographic coordinate systems to understand how we flatten maps using projections. Projections are built on top of geographic coordinate systems, so this knowledge will form the foundation for what you learn next, and I think this is where it really starts to get interesting and practical, so stay tuned with us.